All right, so this is going to be our walkthrough for the assignment titled Extra Power Product and Quotient Rule Derivatives. So we've just got some constants, some power rule problems, and then product and quotient rule. So we'll use whichever rule is necessary. Sometimes there'll be multiple options, so we'll try and use whichever one makes the problem the easiest. First one here is just a really straightforward one. The square root of 30 is a constant, so the derivative of any constant is just 0. And that's it. It's not like 30 to the 1/2 and then you have to use the power rule. Don't do that. It's a constant. Its derivative is just 0. For our second one here, we've got negative 4x to the 10th power. This is just a power rule problem. Remember, our power rule says that the derivative of x to the n is equal to nx to the n minus 1. So we'll just multiply nx to the n minus 1 by the negative 4. So we multiply the negative 4 by 10, giving us negative 40, x to the 9th. We should put our g prime of x there. So negative 4 times 10 is negative 40, and then drop the power by a degree of 1. For this one, we've got a 1/4 times the quantity t to the 4th plus 8, and we're taking a derivative here of something that's in a variable t. We can either choose to distribute the 1/4 through first. So I'll show that first. So if we say h of t is equal to 1/4 t to the 4th plus 2, then we just take the derivative of this, getting h prime of t is equal to 4 times 1/4 is just 1. And so we'll just have t to the power of 3. And then the plus 2 is a constant, so that goes away. The other option, if we want to, is you can just remember that if you have a constant out in front, you can just leave that constant there and multiply it by the derivative of the other function that we're multiplying the constant by. So the derivative of t to the 4th is 4t cubed, and the derivative of plus 8 is just 0. And you can see that either way, we just end up getting t cubed as our derivative. So either way you want to look at it is fine. For this one, we got cube root of x. So what we'll first want to do is we'll want to rewrite this as a rational exponent, x to the 1/3. That way we can just use the power rule. So y will be 1/3 x to the negative 2/3, right? Bring the 1/3 out front, and that third minus 1 is negative 2/3. It's not necessary, but it's good to know that you can drop that into the denominator there. And so this would be acceptable as well. Also to know that this is the same as 3 times the cube root of x squared in the denominator. So any of those answers would be fine. For this one, we got a couple of different things going on here. One, we've got a linear piece. This piece is just linear, right? It's u to the first power times a number, right? Times the square root of 2. So the derivative of a linear piece should just be the slope of that linear piece, right? So that should just be the square root of 2. Then we'll deal with this here off to the side a little bit. That's like having the square root of 3 times the square root of u. And so the constant out in front is just square root of 3. It's like having square root of 3 times u to the 1/2. And so now we can just use the power rule on that. So we're going to have plus after our square root of 2, and then we're going to have a square root of 3 times 1/2, which will be square root of 3 over 2, and then u to the 1/2 minus 1, or negative 1/2. Of course, you can also write this as just root 2 plus root 3 over 2, oops, I said root 3 over 2 root u. So either of those answers would be acceptable. I'd take either one. Doesn't really matter. Okay. Our next one here is just another nice, easy power rule. We know it's a power rule problem because we can see it's just x to some real number power. So that real number just gets thrown out in front. And then we drop our power by 1. So negative 2/5, oops. Negative 2/5 minus 1 would be negative 7/5. For this next one, we have two ways we can look at it. The much more difficult way is to use the quotient rule, but the much easier way is to just simplify this down first and say this is equal to 3x plus 5, right? If I divide 3x squared by x, I get 3x. And if I divide 5x by x, we get 5. And we want to note that like our original function has a domain restriction at x equals 0. So we want to think about that in the context, like if there was a context to this problem, we want to make sure we knew that that our derivative here wasn't going to exist at 0 because the function doesn't exist at 0. The derivative can't exist at a place where the function doesn't exist. But everywhere else, the derivative should just be the derivative of 3x plus 5, which is 3. And if you wanted to go through and use the quotient rule for this, you could. I don't think it's really that necessary, but if you didn't notice to do that, you can see that using the quotient rule, right, it's u over v, its derivative becomes v du minus u dv over v squared. So if we do that, we have x times the derivative of 3x squared plus 5x, which is 6x plus 5, minus u, our numerator, 3x squared plus 5x, times the derivative of x, which is just 1, all divided by x squared. And we'll see that as we go through and distribute this all out, we get 6x squared plus 5x minus 3x squared minus 5x over x squared. The 5x and the minus 5x cancel. 6x squared minus 3x squared is just 3x squared. And when you divide that by x squared, you just get 3. But it's a lot more work to do the simplification and use the quotient rule than it is to do the simplification first. So I highly recommend, if you can simplify the function down first, always do that. So here's another example of one that we could use the quotient rule on, but we are most definitely not going to this time. We're just going to do the simplification first. So 2x to the 2/3 divided by x to the first. Well, that should turn into 2x to the 2/3 minus 1, which is negative 1/3. Right? And again, this isn't the derivative yet. This is just us simplifying. It's just dividing term by term. And so now we'll have minus, and then here we've got x to the, that's x to the 1/2. So if we do x to the 1/2 minus 1, we should get x to the negative 1/2. And so now we've got a much simpler function that we can just use the power rule for to take the derivative. So we've got h prime of x is equal to negative 2/3 x to the negative 4/3 power. And then we've got plus 1/2 x to the negative 3/2 power. And that should be our final answer. Here's yet another one where the simplification before taking the derivative is going to make life a lot easier. So we'll rewrite this as x to the 5/2, because we have x to the 3rd divided by x to the 1/2, right? And x to the 3rd is x to the 6/2. So if you subtract the exponents there, you're going to get x to the 5/2. And then minus x to the negative 1/2, right? 1 over root x is x to the negative 1/2. And so now we'll take the derivative of our nicely simplified function. It'll just give us 5/2 x to the 3/2 plus 1/2 x to the negative 3/2. Again, just using the power rule, right? Multiply that power out into the front and then drop the exponent by 1. For this one, we could use the product rule, but I'm not even going to bother to show it with the product rule because it's just so much easier to distribute it out. Anytime you can, divide like we did in the last few, or multiply to turn something into just a power rule derivative, I highly recommend that. So noting that this piece right here is t to the 1/3, we can distribute t to the 1/3 times t squared. And, t to the 2nd power is 6/3, right? So 6/3 plus 1/3 should be 7/3. So we have t to the 7/3. and then t to the first right here, which is t to the 3/3 times t to the 1/3 should be t to the 4/3. And then t to the negative first power, that'd be negative 3/3 plus or times the t to the 1/3, you add the exponents. So you should get plus t to the negative 2/3. And again, that's just the simplification out in front before we actually take our derivative, f prime of t, which should be 7/3 t to the 4/3 using the power rule on the first term. And then our second term should be 4/3 t to the 1/3, again using the power rule. And then our last term should be minus 2/3 t to the negative 5/3, once again using the power rule. So always simplify first if you can. All right, on to the next one, x plus 7 over 3x minus 1. There's not a great simplification to do here. In fact, there's not really any simplification to do here first. So this time we're going to use the quotient rule, u over v. I'm going to write out what the rule is, right? The derivative of u over v using the quotient. I should probably spell the quotient correctly. Let's try that again. The quotient rule says you take the denominator, v, multiply it by the derivative of the numerator, subtract the numerator times the derivative of the denominator, and divide it all by the denominator squared. So our derivative will be, first off, the denominator, 3x minus 1, times the derivative of the numerator. Well, the derivative of x plus 7 is just 1, because the derivative of x is 1, and the derivative of 7 is 0. And then we will subtract that numerator, u, so x plus 7, times the derivative of the denominator. The derivative of 3x is 3, and the derivative of minus 1 is 0, so we don't need to put that. Then we'll divide everything by 3x minus 1 squared, right? Our denominator squared. And so now we should just be able to simplify this down. We have 3x minus 1, and then as we distribute the minus sign and the 3, we'll get minus 3x minus 21 in our numerator there. And the denominator still got 3x minus 1 squared. We should see that minus 3x and 3x cancel out. Negative 1 minus 21 ought to be negative 22 all over 3x minus 1 squared. All right, for our next one here, v of x, we've got one function being multiplied by another function. So we could go and use the product rule on this one, but I think the easiest way is just going to be to distribute it out first. So don't use the product rule on these like binomial times a binomial, unless you just really, really want to, because the simplification afterwards requires a lot more distributing than if you just simplify it out first. So this should be 2x to the 7th if you multiply 2x cubed by x to the 4th. If we multiply 2x cubed times negative 2x, we should get minus 4x to the 4th. And then we should get a plus 3x to the 4th from 3 times x to the 4th. And then lastly, we should get a minus 6x there. And if we simplify that down, we can combine the like terms here. We should get 2x to the 7th, right, minus x to the 4th minus 6x. Okay. And so that should be our new function that we're looking at, or the simplified version of our function. And now we'll take the derivative v prime of x, just using the power rule. Should come out to be 14x to the 6th, because 2 times 7 is 14, and we drop the power by 1. And then minus 4x cubed, again with the power rule. And then the linear piece just becomes its slope, right? It's still the power rule, right? Which just becomes minus 6. And there is our derivative. For this one, u of x, again, it's not, it's not like we couldn't use the product rule here, but I think it's going to make things a lot easier if we choose not to use the product rule, if we just choose to distribute first. So x to the negative 2 times x to the 5th, add the exponents, gives you x to the 3rd. And then x to the negative 2 times negative 2x to the 4th, that minus 2 stays, and then add the exponents. Negative 2 plus 4 is x squared there. When we do x to the negative 3 times x to the 5th, we'll just, again, add the exponents. So plus x squared, and x to the negative 3 minus 2x to the 4th. We'll keep the minus 2 and add the exponents to just get minus 2x. And we'll combine the like terms, x cubed, and then negative 2x squared plus x squared should just be a negative x squared, and then minus 2x. And now we have a simplified version of u of x, which is much easier to deal with because we can just use the power rule. Derivative of x cubed with the power rule is 3x squared. The derivative of x squared with the power rule is minus 2x. And then the derivative of minus 2x is just the linear piece, minus 2. So we got 3x squared minus 2x minus 2. All right, for our next one here, there's not a nice simplification on this one, so we're just going to have to go through and use the quotient rule. So I'm going to remind ourselves here, we have u over v. I'm going to put the quotient rule up, v du minus u dv all over v squared. And we'll just go in and put everything into it. So first of all, we put our denominator, root x plus 1. Right, y prime. Y prime is v times the derivative of u. Well, the derivative of 3 root x minus 1. And we have multiple different ways we can write that. We can either write it like the rule that we learned, right, that the derivative of root x is 1 over 2 root x, which is what I'm going to use here. This becomes 3 over 2 root x. And then the minus 1 just goes away because the derivative of minus 1, that's constant, it's 0. So we have v du minus, now we have u, so that's 3 root x minus 1. And then we need the derivative of v, which, well, the derivative of root x, as we just said, is 1 over 2 root x. And then the plus 1, that's a constant, so its derivative is just 0. We'll divide that all by our denominator, root x plus 1 squared. Be careful not to accidentally extend that square root over. Just a lot of people do that. Those are completely different expressions, so don't. Now we can just kind of simplify out that numerator. So 3 over 2 root x times root x. Well, the root x over the root x will just cancel, so that's just going to end up being 3 halves. And then we've got the 1 times the 3 over 2 root x. Well, that's just plus 3 over 2 root x. And then as we distribute the other pieces out, we've got a minus 3 over root x times a 1 over 2 root x, so the root x's will cancel, so that just becomes minus 3 over 2. That's nice because that looks like it's just going to cancel out with the 3 over 2 that we had. And then we do the minus 1 with a minus in front, so it's really a plus 1 times 1 over 2 root x, so plus 1 over 2 root x all over root x plus 1 squared. And we can see the 3 halves and the minus 3 halves should cancel out. And we're left with 3 over 2 root x plus 1 over 2 root x. Well, if I have 3 of something and then 1 of something, that'd be 4 of that thing. Right, so that'd be 4 over 2 root x, all divided by our root x plus 1 squared. And from there, we can just simplify the 4 over the 2 as a 2. And we've done this a few times where we can look at this as over 1. And then when we multiply by the reciprocal, and it's a fraction over a fraction, that root x and that root x plus 1 squared will end up in the same denominator. So this is 2 over root x times root x plus 1 squared. And that should be our final fully simplified answer. For this one, once again, because we don't have a singular term in our denominator like we did with some of those earlier ones, we're going to have to just use the quotient rule. I guess I'll write it up here again, just I think it's good to see it. We have v du minus u dv all over v squared, right, where our function is written as u over v. So our function's derivative, g prime of t, ought to be the denominator, 4 plus t squared, times the derivative of 2t, which is just 2, so v du, and then minus u, which is 2t, times the derivative of v, the derivative of 4 is 0, and the derivative of the plus t squared is just another 2t. We'll divide that all by 4 plus t squared, and then we will simplify down. So in our numerator, 4 times 2 is 8, right? And we distribute, and then t squared times 2 is 2t squared. And then minus 2t times 2t would be 4t squared all over 4 plus t squared. And of course, 2t squared minus 4t squared is just going to be negative 2t squared. So we have 8 minus 2t squared over 4 plus t squared. And don't make the mistake I just did that we're going to fix, which is that denominator needed to be squared. Right, so we go through and square all of those, and we end up with our good final answer of 8 minus 2t squared over 4 plus t squared squared. And I know you can factor a 2 out of the numerator. If you want to do that, go ahead. And then you can even factor that as a difference of squares up there in the numerator, but there's no real reason to do that because it doesn't cancel with anything in your denominator, so I wouldn't bother. Another one here where we're going to have to just use the quotient rule. So we'll write it out once again, u over v, and our derivative is going to be v du minus u dv over v squared. This time I'm going to actually remember to square my denominator right off the bat instead of having to go back at the end. So f prime of x should be v, x squared plus x plus 1, times the derivative of u, which is just 6x, right? The derivative of 3x squared with the power rule would just be 6x, and the minus 1 goes away. So there's v du minus u, 3x squared minus 1, times the derivative of v, the derivative of x squared is 2x, the derivative of the x is just 1, and the derivative of the plus 1 is 0. And then it should all be divided by our denominator squared. Okay? Now we'll just distribute out the numerator and simplify. So x squared times 6x is going to give us 6x cubed. X times 6x is going to give us 6x squared. 1 times 6x is going to give us 6x. A 3x squared times a 2x is another 6x cubed, but we got a minus sign in front, so we'll make that a minus 6x cubed. Then we're going to have a minus 3x squared with the minus out in front. That's a minus 2x, but then when we put the minus in front, that'll be a plus 2x, and that's a minus 1, but when we put the negative out in front, it'll be a plus 1. And then we'll throw our denominator squared in there, and all that's left is to combine the like terms in our numerator. We've got a 6x cubed with a minus 6x cubed, so those ought to cancel out. We've got a 6x squared with a minus 3x squared, so that ought to be 3x squared. We've got a 6x with a 2x, that ought to be 8x. And lastly, we've just got the plus 1, and it's all over x squared plus x plus 1 squared. All right, just 2 more to go through here. So here is h of x is 1 over 5x squared minus 3x. So this one is a quotient, but it's also the reciprocal of a function, and we had a rule for the reciprocal of a function. This is a reciprocal. I'm going to write this here, right? The reciprocal rule. Right, the reciprocal, that's not an L. I don't know what I'm doing here. The reciprocal rule says that if I want the derivative of 1 over some function, right, or we'll call it a constant because this works for any constant, over a function, that we just do negative of the constant times g prime of x over g of x squared. And this is exactly what you get if you were to do the quotient rule with a constant up in the numerator. So we'll just use the rule. H prime of x should be negative of our constant, which is 1, so I don't need to bother to write that. And then our derivative of 5x squared minus 3x, that should be 10x minus 3 when we use the power rule on that. And then we just throw our denominator squared down there, and that's it. We're just using the reciprocal rule. If you want to go and use the quotient rule, that's fine. But when you do, note that your du, right, your derivative of 1 is 0. So it just cancels out that v du, right? We normally have v du minus u dv over v squared. So all we end up with is du is 0. So that term is 0. And we're just left with the negative of u, which is our numerator, which is our constant, right? So that's our negative constant times the derivative of the denominator over the denominator squared. So it'll work out the same either way. All right, and here's our last one. It's another reciprocal rule problem here. So we're going to say this is negative constant times g prime of t this time over g of t squared. So all we have to do is go straight through and use that rule. That rule says that s prime of t ought to be the opposite of our constant, which again this time is just 1. Our derivative of our denominator there should be 3t squared minus 2t minus 1 if we use the power rule on that. And then we just throw in our denominator squared. And that should be our final answer. And once again, you could use the quotient rule for that one if you want to, but you don't really need to. This will be perfectly acceptable and work every time. So that's it.